Alright, so let's talk about resonance structures. And of course, like any good instructor, I'm gonna begin talking about resonance structures by not talking about resonance structures. I have to tell you something first that will help us, navigate the world of resonance structures in a much more amenable way. Alright, so this is something known as the bond line formula. It's something that you typically use a lot in organic chemistry, but I'm gonna show it to you right here so that you get an idea of what it is, and not only that, but you get to use it. And with that information, we'll then tackle the resonance structures themselves. So what you can see here is a bunch of hydrocarbons. You have carbon bonded to carbon or carbon bonded to hydrogen, and you have different levels of molecules. Pretty much this is a 2 carbon chain. Over here we have a 7 carbon chain, and the last one is a very long 18 carbon chain of hydrocarbon. Now as you can see, the longer this chain gets, the more annoying it is to write those extra H2s or H3s that a carbon has. The idea with the hydrocarbons is that you basically have 4 bonds, or you have to have 4 bonds on every carbon in order for the carbons to have a full octet. And you must remember that carbons are second row elements, so they have to fulfill the octet rule. So what you can see here in this structure, for instance, if you look at the carbon that I'm highlighting here, it has 2 carbon-carbon bonds, and each of those bonds contains 2 electrons, so that gives carbon 4 electrons altogether. In order for it to complete its octet, it needs to have another 2 bonds to fulfill its octet. And that's the reason why it has 2 hydrogens, because each of those hydrogens is present as a CH bond, and each of those bonds contains 2 electrons. Now, with all that information given, we can actually make the drawings a lot easier to the eye. And specifically what we do is we technically rewrite them in the same shape in which you see them, but we omit writing any of the hydrogens or any of the carbons present in the molecule. So notice this molecule C2H6, instead of writing all those elements out, all you have to do is draw a line. And it's understood that the ends of the lines represent carbon. And not only that, but those carbons have enough hydrogens to fulfill the octet rule. Same thing goes for this molecule, C7H16. If you get rid of the hydrogens and carbons and simply keep the structure as is, then you end up with this wiggly line, which basically each corner or each end of the line, right, but each corner also represents a carbon. And like before, depending upon how many connections this carbon has, like if we look at the carbon here on the left, this carbon only has one connection to one other carbon, so it needs 3 hydrogens to fulfill its octet. So another way to put it is that each carbon has to have a total of 4 bonds to be happy. And that's the whole premise of these accounts. Look at the carbon here in the middle. This carbon has 2 bonds to other carbons, so it only needs 2 bonds to hydrogens to complete its octet. And of course, the last molecule that looks pretty ugly because of all the carbons and hydrogens, once you get rid of all of the atoms and simply keep the skeletal framework, the bond line formula, this looks a lot easier to digest. Alright, but as I was saying, the number of hydrogens on each one of the carbons present, which is either an end point or a corner, is going to be given by subtracting the number of connections that the given carbon has from 4. Alright, now just to give you a clear idea of what that is, I'm showing you here a molecule that contains a lot of carbon in it. Pretty much every end represents a carbon, every you could call it intersection even, represents a carbon, every corner represents a carbon. Now the only things that are not carbon are literally elements that you have to write out. So anything other than carbon and hydrogen you do need to write out. Like oxygen needs to be explicitly written out, bromine has to be explicitly written out, and any other element other than carbon and hydrogen you do need to write down. But as far as carbon and hydrogen, those 2 elements you can omit from the drawing, just keep the skeletal framework. Alright, so this is what we're going to do. We're going to look for carbons that contain only 1 hydrogen in them. And in order for that to be the case, the carbons that we're looking at must already have 3 directions arising from them. Okay, so let's take a look. If we browse quickly through the molecule, we'll realize that the following carbons must contain a hydrogen. Now let me show you that again. The carbon over here has 3 directions already coming out of it, so you can only have a hydrogen left over. Carbon right here has 3 directions coming out of it, so you must have a hydrogen. This carbon right here has also 3 directions, so you must have a hydrogen. Carbon over here, 3 directions, so you must have a hydrogen. Carbon over there, 3 directions, so you must have a hydrogen. Alright, so that looks pretty good. So all the carbons here definitely have one hydrogen because the carbon itself already has 3 directions arising from it. If you have 2 directions, or if you're looking for 2 hydrogens in a carbon, then you definitely need to have 2 directions arising from it only. So we could, if we browse through the molecule, we'll see, okay, this carbon right here only has 2 connections to other carbons. So that one will have 2 hydrogens within it. The carbon right here also only has 2 connections, so that will have 2 hydrogens as well. The same can be said for the carbon here on the left side of the hexagon. And yes, we also have the one right here with 2 hydrogens. Alright, now if we're looking for carbons that have 3H's, then we're basically looking for carbons that have only one direction. And to put it simply, these are carbons that are going to be at the end of the molecule. So this end right here, that end over there, end right here, end right there, this end, and that end, they all have 3 hydrogens because they are only connected to one other carbon. And finally, the carbons that don't have any H's already have 4 directions coming from it. And if you look carefully, you realize that there's a carbon that fits that profile, specifically the carbon here on the right side. This carbon already had 4 directions to begin with, so it does not need any hydrogens in order to fulfill its octet. Alright, so this is the way the bond line formulas are going to work out. And this is what we're going to use to explain resonance structures. So you may remember from the last video I did mention that for you to have a resonance structure you have to have an atom with lone pairs, which is next to an atom that contains a multiple bond. And if that's the case, then you can bring the electrons from the neighboring atom onto the multiply bonded central atom. And the electrons that used to be part of a double bond for atom Y have to get out of the way, forming the resonance structure right here. Alright, I even talked about the idea of having electron deficient centers. That's a possibility, but we're not going to investigate that too much in this class. But just keep in mind that, yes, if you have room available in your central atom, you can definitely accept electrons. Alright, so this is the way it's going to go. Here I'm showing you the bond line formula of a hydrocarbon. And the first question you want to ask yourself when you see a molecule like this, specifically if there are multiple bonds present, what you want to ask yourself is the question as to whether there is a neighboring atom with lone pairs next to multiple bonds. And if we look through the structure very quickly, you might zone in on this oxygen. You have a multiple bond and there are the lone pairs. The problem is that that atom is not next to a multiple bond, it is in the multiple bond itself. So you don't want to start a resonance structure right there necessarily. But if you look over here, we have an oxygen with lone pairs, and next to that oxygen there's a carbon with a multiple bond. So we're going to focus on this particular part of the molecule. And as the drawing here depicts, we're going to bring electrons, the lone pair electrons from the oxygen onto the carbon, just like that. And the moment that happens, the lone pair electrons, the double bond electrons that used to be part of the carbon have to get out of the way onto the neighboring electron. And it is of note that this is happening with a triad of atoms. It's always going to take place with 3 atoms. One set of electrons comes in into the middle one, another electron set comes out from the middle one. Okay, so when this happens, pretty much what takes place is that this oxygen with the lone pair now becomes an oxygen double bond. And the double bond that used to be here now has ejected its electrons onto the adjacent carbon, thus forming the following structure. Okay, so aside from the fact that we have drawn a new electronic configuration, if you will, for the molecule, we've also developed some charges because the oxygen that used to have 2 lone pairs now only has 1. It has, in a way, given away its electron pair, and because of that it has developed a positive charge. On the other hand, the carbon here used to be without lone pairs, but now it has a lone pair, so it has received electrons and now it has a negative charge. Alright, now when you draw your new resonance structure, here's where you have to ask yourself the question: is the new lone pair next to multiple atom? And you might say, well, yeah, there it is. The multiple bond atom is right here. But if you actually try to draw a resonance structure with that, you'll go back to the original structure you started with. So what you want to do is kind of keep the same flow in direction as you started. So we started kind of going to the left in the structure. We're going to keep going towards the left. So really, the question is this lone pair next to multiple bond towards the left side? And sure enough, there is a multiple bond there. So as you might have guessed it, we're going to move those electrons over to this middle carbon, and the electrons that used to be part of the double bond will have to get out of the way, thus forming the following structure. And check this out. The negatively charged carbon gave away its electrons, so its charge went up to 0. So now it's neutral. But the carbon here on the end received electrons, so now it has a negative charge along with the lone pair. Alright, now same question. Is this lone pair next to multiple bond? And the answer is yes, there is a multiple bond, a new multiple bond. So we're going to move those electrons over to create another multiple bond, and the multiple bond that used to be there will have to get out of the way onto the next carbon. So notice the sequence: 1, 2, 3 carbons. And also notice that when we actually move the electrons to reform the new multiple bond and form the new lone pair on carbon, also the charge is swapping from the first position to the third position, and that's kind of the case in every single structure here. Alright, now same idea, lone pair next to multiple bond, and sure enough we have a multiple bond right here, so we can bring the electrons down and kick these electrons out of the way, and in the process we'll form yet a new structure. And then you ask yourself the question: is there a multiple bond next to the lone pair of electrons? And the answer will be no, because this is the terminal atom and it has nothing next to it. But if you look carefully, you realize that going back to the structure, there's actually 2 ways to go about drawing a resonance structure. We could have gone the way we did to get to the structure here, or we could have gone down because there was another multiple bond there. So if we do that and we bring the lone pair of electrons here and kick these ones out of the way, we end up yielding the following structure. And altogether, the structures represent pretty much the same picture throughout the entirety of the structure. These are all resonance structures of each other. So hopefully this will guide you in approaching the problem in future assignments. Okay, in the next video we'll talk about Vesper theory.